Okay. So let's continue. Okay, so let's spend like 1 hour to talk about the coding part of this convolutional neural network. So so let's start from the handwritten digit recognition as well. So you should so basically for this problem, so you have 60,000 image of handwritten digits, then 18 by 18 to have 8. So here, so basically it's all the image of 8. So basically, if you want to utilize convolutional or CNN to do the handwritten, to do the digit recognition, okay. So here's something we want to, we need to do. So CNN using Python. So that means there's no TensorFlow, there's no third-party library. Then if you want to do that from scratch, so here's some architecture we are going to use. So basically, so the main point will be example.py. So that's basically give you the main entrance of the network of the whole library. So I share this code through the Google Drive. So you can download and you can run through that. But you need to, before that, you need to do the you need to read the readme.md. So it basically give you the so the examples how could you use this code. So the entrance will be here, and then the data set will be stored in this folder. Then we have a few, as you can see here, we have a few Python files. For example, you have a network class, layers class, or functions, a few other functions. Function basically including all the activation functions you are going to use. But anyway, so you need to install the PIP3, Python 3, nmpy. Then when you try to use the code, so basically you in cd the src, that's the src, it's the whole fold. Then you can in the command line, so you can run Python 3 examples.py, and then you can specify the data set you are going to use, mnist.mpz. So then you will specify the second parameter, so that's a fully convolutional layer or convolutional layer, okay, convolutional network. So it's basically, you have two options. One is the FNN, one is the CNN. You can call this two examples. So so as you can see in the examples.py, so we have so here's the main coding line we are going to use. So basically we will use all these modules as a self-defined modules in the same folder. So the CNN01, so that's the first convolutional network architecture we create. Okay, so for example, if you read the architecture here, so basically you have, for the input layer, you need to specify it's a 28 by 28. Okay, then you have the second layer as a convolutional layer. So then you have the kernel size. Then you need to do the activation function to be specified that to be f.sigma. We use the sigma function to define that. Then you specify a max pooling layer, and then you have a fully connected layers. Okay, so it's the height is 10. So basically, then you have the 10 means so you have the 10 units. Okay, that's the output layer. Specifying the output layers. So basically the output layers, you have a 10 neurons, then you specify the softmax as the activation function. So basically, so once you create this net, okay, and then you will specify the optimizer will be the SGD, it's a stochastic gradient descent. So 0.1 will be the learning rate. Okay, so you specify this optimizer, then so basically you just create one variable for structure variable net, another structure variable optimizer, and then you return this two variables plus a few other variable like the number of epoch. So it's 3 means you will access all the training sample 3 times. So each training sample you access 3 times. So 3 sweeps. So remember, so when we talk about the gradient descent, we will use a mini batch, right? So let's say you have 1,000 training sample. Every time I use 10 samples. So I use this 10, another 10, another 10, another 10. You keep doing this until every training sample will be accessed by 3 times. Okay, then you will stop. It's 3 epochs. So the batch size will be 10. So you have a 4 parameter here. So network, optimizer, number of epochs, or batch size. So you're given this 4 parameter, you will call the network.train. So you can see here, so the N will be the network layer, network class of a function, a module, and then we call the function train. So you're given all this parameter. So it's going to be, you have the training set, you have a validation set, and then you will train the network here. And then you will call the end test, and then you have the testing set, and this will return the accuracy. So the main point will be the network layer, okay, network class. So basically, so that's the major function we are going to use in this scripts. One is how could you make predictions. Another of course will be how to learn or train the network from data set. So for predictions, it's more about testing. Okay, for testing, it's pretty much like how would you perform. So you are given the network. Say for each layer, you know the parameters. Then for each testing data, so how could you get the prediction? So that's pretty much a feed-forward neural network, right? The feed-forward path. So basically, for each X and Y in the testing data set, okay, so we do the net the feed-forward. We call the feed-forward, and then we'll, yes.
Forward propagation.
Yeah, it's a forward propagation or forward path. Yeah, you do the forward path, then you got the prediction.
Loss.
Yeah, the loss. No, not the loss, the prediction. The prediction, you compare the prediction with the loss, then you, with the ground truth label, you got loss. Yes. But here, there's no backward path involved because we only care, okay, if you run the feed forward path, then you will, let's say, the np.argmax net the output layer .a. That means that's the activations for the output layer, right? Then you will compute. Remember, for this case, the output layer you have 10 units, you have 10 predictions. So argmax basically will try to find out which prediction is the maximum one, right? 1 or 2 or 3. So then you have the prediction here. So this gives you the prediction which class so this sample belong to. And then you compare whether it's equal to the argmax Y. So Y will be the ground truth label. Okay. So you compare whether this guy is equal to the ground truth label. If it is, then your accuracy equal, you will count 1. Okay, you will count 1 for the accuracy. So eventually, for every single sample, you will count 1 if it's correct. Then eventually you divide it by the number of samples. So this kind of return the accuracy. Okay, so that's the test function. So the key function will be the feed forward. Okay, if you look into the network feed forward basically is a forward path. Okay, so you have the X as input, and then you will so you will set input layer dot z equal to x, input layer dot a, so z will be the linear combination, a will be the nonlinear transform outcome, as I introduced last time, right? So for the input layer, both will be equal to x, so that's no nonlinear transformation. And then you call the for each layers. Look here. So for each layer, so for each layers, you will call this layer. So layer will be the another class. Okay, the layer class. So layer class you will call the feed forward function, say the forward pass, and then so basically you can and with the previous layer as as the input. So basically this function will finish the a single layer feed forward pass. Okay, a single step of the feed forward pass. So from this layer to next layer, then you will do the linear combination, you will do the nonlinear transform. So anyway, so the layer will be defined by in this function. So convolutional layer dot feed forward function. Okay, if you consider this function, it's going to give you so remember the previous layer will be the input. The current layer is defined in this class itself. Okay, so basically, if you check this this implementation, so it's kind of a recursive definition. Okay, so basically, you will look into the self.z. It's going to give you the linear combination between the layer width and the inputs from the previous layer. Okay, the inputs from the PREV slash layer. Okay, so basically you check this for loop. So basically, so for each possible filters, and then for each possible activation map, and then for each possible, so basically for each filter, for each activation, then you have the filter, then you have the convolution between this filter and the sub window of the previous layer. Okay, so if you check this, so this gives you the exactly implementation between. Okay, so the coding line I circle around. So make sure you look into this code because it's giving you the exact implementation for the convolution between each filter and the input layer. Okay, so and then you have the self z. Look into here. So this guy is also very important. So for each depth, for each layer, remember if you have 10 filters, you are going to have a 10 activation map. Then for each activation map, okay, then you will do the convolution with the current filter. Okay, with the next layer, the filters of the next layer. So after that, then you will take a sum over all this activation map. Okay, remember, for each filter, the filter will be expanded so that you have the same depth as the input layer. Okay, if the input layer is 32 by 32 by 10, then the filter will be 5 by 5 by 10. Okay, so that's why you get a self z. So you kind of put all the the activation, all the dot product together, then you have the z. So this gives you and then you have look into here. Once you get z, then you will call the activation function, and then taking the z as the input. So that's the linear combination. You use it as this activation function, so this gives you the nonlinear transform. And then you got a self.a. Okay, so self.a will be the input with the output of this layer. For this step during the forward pass. Then you run the function for the next layer, next layer, next layer. For each layer, you will do this with the previous layer, and eventually you got the forward pass. Okay, it's clear, right? So basically, just let's repeat. So you start from the test. Okay, you start from the test, then you call network.feed forward. You start from the first layer. So X will be the first layer, right? And then you will call the network.feed forward layer. Basically, they call they consider each layer as one object of the layer class. Okay, and then for each layer, okay, and the previous layer, you will call the current layer feed forward with the previous layer. So it's an iterative process. Okay, so for each current layer, you will do the feed forward by using the previous layer. At the first step, the previous layer will be X. The current layer will be the first hidden layers. And then once you get the outcome of the first hidden layer, then you will repeat this process. Okay. So we are good for this part. So that's for the testing. So that's the code. The main component will be here. I mean, really hope you read this, just a few lines of code. Okay. So you know exactly what happened. Okay. So you have conceptual, you know, it's a feed forward. But here we need to know the, say how could you implement in your coding. So when you're for the training process, it's also exactly the same as the as what we introduced before. So basically, for each patch, so look into here. So you do some processing here. So you have an input. You have for each epoch. Okay, remember you have 3 epoch, and then you will call the random shuffle function. So basically, you will randomly arrange all the training samples. Then you randomly pick up, randomly divide this arrangement into few mini patch. Let's say if the total numbers is 1,000, you randomly arrange this 1,000 samples. Okay, then you divide every then you divide the whole 1,000 sample into 10 into 100 mini batch. So each mini batch will have 10 samples. Okay. So anyway, so you have the batches here. Okay. And then for each batch, you will call the network dot back propagate. Okay. So then you call this function, and then so once you do the back propagate, then you will finish the training process. Okay. Every time you do the back propagate, you will update the network parameter as well. So the key function will be the back propagate function of the network class. Okay. So the network class. So here's how you implement this. So the network this function. So if you look into here, so same thing. So basically, when you do the backward parse, so we will count the layer. So that's a layer class. So we'll do that layer by layer. So we start from the last layer. Okay, we start from the last layer, and then we compare. Look into here. So for X, Y in batch, then we do the feed forward first. It's a forward pass first. Okay. Then you got all the way to the prediction. Then you compare the loss function. You compare the self.output layer.a. So that's the activations you got for the last layer. Then you compare that with the y. That's the label y. Okay. Then you got what? You got a loss. So once you get the loss, and then I will, the data will be, so look, so it's a loss times the output layer the DER activation function. That's pretty much the derivative of the activation function. That's a local gradient. Okay. For the last layer, remember, you also have two parts. One is the global gradient, one is the local gradient. So the global gradient for the last layer will be the loss. And then the local gradient will be the derivative of the activation function with respect to the width. Okay, so that's why you have a loss times by, this derivative activation function. It's determined by which function you have. If you use the sigma function, so this guy will be 1 minus sigma function times sigma function. Okay, anyway, so you have this loss, the delta here. Okay, that's the gradient for the last layer. So again, for previous layer and the layer or the current layer, in all the layers. So for each layer, you store as a layer variable. And then for the previous layer, you stay in the prev/layer. And then you will call the layered back propagate function. So you will do it's just like the layered feed forward propagate. Okay, so here we just finish. Given this layer and the previous layer, how will you do the feed forward propagation? So once you have to do this propagation method, so remember, because you already know, so you will have the derivative W and the derivative B. So that's kind of the gradient for W and the gradient for B. Okay, and then you will accumulate this gradient together. Okay, so you have the sum derivative W, sum derivative B. Okay, clearly this all matrix, or everything we are talking about are matrix. So you need to imagine, so the W will be all the weights between current layer and the previous layer. Okay, the B of course will be the vector. Okay, so determined by how many filter you have. If you have 6 filters, then you have a 6 bias term, right? It means by how many filter you have. So I really hope you check the dimension. Okay, remember, so when you run this code, you can put a breakpoint here. Okay, and then try to understand the dimension you have. Okay, for each layer, you begin from the first layer, then you try to understand the self-feed forward X, and then you begin from the last layer, you try to understand the dimension of loss. For example, clearly it's going to be a single value. Okay, loss will be single value. So the output layer, the DER activation function. So this guy is going to be, the dimension will be related to the how many filter you have for the last layer. It's going to be 10. Okay. Check the dimension. It's again, so this will be the key components. Okay. For given one layer and the previous layer, how would you do the propagation between that? Okay. How would you do that? So this gives us some, so basically, so I will skip this because it's a very similar, I would say, it's very similar to the feeder forward neural network. So remember, okay, so when you do the forward pass, so you will have a linear combination and then you have the nonlinear transformation, say sigma function. When you do the backward pass, you will have the you will have the loss or the global gradient, okay, times by the derivative of the activation function. So it depends on what kind of activation function you have. If you have a sigma function, then you have the inverse, we call the deriv DEV sigma function. Okay, so that's just another function. Then you have a max, let's say the hinge loss. Then you will check the prediction whether it's larger than 0 or smaller than 0. If it's larger than 0, you just have a linear gradient. Okay, so it's very, I mean, it's not so complicated if you understand the material we introduced in the slides. So you can compare the concepts over there to this code. So it's just a couple lines of code. Okay, so then you call the function sgd.apply. Okay, apply, basically you will update W. Okay, so basically when you try to, so here's the key point. So you update the gradient in the network, the backward parse. So for each 2 layers, for every pair of layer, so you will update the derivative W. And then eventually you will call the apply. Apply means, so given these layers and given this derivative or the gradient, so I want to update the parameters. Okay, update the weights. So this gives you the how we update. So look into here, it's very simple. So when you apply this, you will, for each layer, then you will take the gradient, okay? Again, it's so many, it could be a tensor here. So you take the gradient, then you update, okay, you update this W by the learning rate times this gradient, okay, learning rate. So this is exactly the update equation we talk about. And then same thing, you will do that for the bias term, okay, for the bias term. So make sure you check the dimension here, because the dimension of W will be a tensor, okay, it will be a tensor. It's going to be like let's say it's 28 by 28, then you are going to have 28 by 28 by how many channels you have. It could be 10, could be 200, it could be more than that. So basically, then you have this, but you will update them together. Okay, so that's a gradient. Okay, that's a gradient to apply. So in brief, okay, if you check the architecture, so in the example, so we basically have we define the network architecture. Okay, and then so this function we'll call network. Okay, you create, so this will be a class. So you create an object of this class. Then this object will store all the network parameters. Okay, so the network will call layers. So when you run the feed-forward parse, so you will call for every single layer, you will call the feed-forward propagation. And then when you try to learn the backward parse, then you will call the layers. So this function, you have 2 very important functions. One is the forward propagation, one is the backward propagation. Okay. So this gives us so you need to check this function a lot. So the layers will call the function optimizer, because optimizer basically gives you if you follow the gradient descent, so optimizer will implement the updated equations. Okay, so let's give you 1, 2, 3, 4. These are 4 major files. Okay, so if you check them, then you have the whole picture about the implementation of convolutional neural network. Okay, I think that's the best we can do in the class, but we do need you to, if you it's like a 90% chance. So you in your practice, in your project, you never write a neural network like this. Okay, you never had a chance to write the network from scratch. But the thing is, if you can understand this, then you have a much better understanding or feel when you have some error message from the the TensorFlow or the Caffe. Okay, so that's very important for you to develop the sense. So here's the these files. Okay, if you look into them, they're not so complex and complicated. Okay, there are only a few paragraphs of codings as the main coding line. Okay, but actually, if you I say you never have a chance to use this for practical project, because in practice, okay, when you try to implement the learning process, let's say, or the training process, you will run into many problems. Okay, like gradient shrinking, like your gradient descent doesn't work properly. Okay, for some reason. Then we need to diagnose, so why your method doesn't work, and then how to solve them. So this list, okay, the list I show you here is pretty much the most common practice that people believe. You have to follow these principles. Otherwise, you are going to run into troubles. Okay, so you can see it's really it's not an exhaustive list. Okay, sometime later we are going to come back and introduce why, how to address each particular problem. But here I just give you an overview, so you know the convolutional neural network. The people are still working on that in academia. Okay, because there are so many open problems. Okay, so the first component will be the activation function, as I introduced before. So the activation function, let's review a little bit here. So for each neuron, you have an input here. So for each input, you have a weight. Then you have the choice of, say, which activation function you want to use. So here, so here's the whole list. All the possible, it's not all the possible, it just gives you the most common, most popular one. So this guy, the ReLU will be the one of them. Okay, so you have the you have the linear combination, you just compare that to 0. If it's less than 0, then you set it to be 0. Otherwise, it's the combination itself. Okay, so then you have a tangent, you have a sigma, you have a leaky ReLU. Okay, so why would you need this? So the sigma function, okay, if you use the sigma function, then you are likely to run into some troubles because it's a saturated neurons. So for some saturated neurons, if for some neuron, if the weights are not properly designed, are not properly initialized, let's say you have a very big weights. That means what? That means you always go too far away from the 0. Okay. If you have a bigger weight for this neuron, the activation will be always here or here. That means it could be either to be 0 or to be 1. So the activation or the map. So whatever input you have, whatever training sample you have, then the output will be always to be 1 or 0. Then what happens? You will kill the gradient. Okay. If the gradient you got is not reflecting the data set, the data input anymore. It becomes some constant value. Okay, whatever data you have, you got the same gradient. So that's why the sigma function. So when you try to, if you use the sigma function as the activation function, you should be really careful about the initializations. Okay, some bad initialization will make the gradient descent stuck. Okay, get stuck somewhere. Then the sigma function output are not 0-centered. It could be, it's not 0-centered, it's not so good. Exponential is a bit computational expensive. Okay, so when it's good if you deal with shallow architecture. If you have like the LearnNet, that's fine. You only have 7 layers. Each layer you only have like hundreds of parameters. But if you use the Google Net, that's millions neurons. Okay, and for each neuron, if you do the exponential, okay, that's a float computing. In CPU, you are going to use a lot of instructions to do the float computing. Okay, so that's why sigma function is not popular. Okay, to summarize, sigma function and the tangent function, they have the same issues. The tangent function, you are always saturated when it's away from 0. Okay, if the combination to be away from 0, you got a constant gradient. So the ReLU function, okay, ReLU function is good. Okay, so it's a rectified linear unit. It's pretty much a linear unit, okay, but it's a rectified. So it does not saturate, okay, because it always give you the different results. Okay, if you have a different input, I always give you different output. That's good, okay, that's good. That's always mean you have gradients, okay. So the second one is computational efficient. Okay, so when a linear combination, when the x is less than 0, you don't do any computation for the gradient. They converge much faster than the sigma function. Why? Because some of them will be directly pruned. Okay, some of the activation function will be killed even before the before running the gradient descent. Okay, so that's why they can converge much faster than the sigma function. Always, even you have a better initialization because you always have a gradient. Okay, so you know how bad it is. Then it's converging much faster. But you also have some issues. Okay, the people call this the dead ReLU. So dead ReLU means will never activate because of 0 gradients. That means what? If you have a bad initialization, imagine, okay, so you always got a 0 or less than 0 activation from previous layer. If you always got x to be less than 0, that means your gradient is always 0. Okay, you have the same trouble as the sigma function. Okay, the sigma function problem is you always have the constant. It could be 0, could be 1. But here you got the trouble for it could be always to be 0 if you have a better initialization. So that people call it dead. It's a dead ReLU. So dead ReLU means the gradient descent doesn't work. If you run like a millionth time, a couple of days, eventually you got nothing. Okay, you got nothing. So how could you resolve this issue? So people call it a leaky ReLU. Okay, so instead of compare x to 0, you compare x to be 0.x, okay, 0.1 times x. So that means if even x is smaller than 0, you still have very small response. Okay, it's not a 0, but it's very close to 0. Okay, it's 0.1%, 0.1 times the original x. Okay, so basically in this case, they call it a leaky ReLU. So that means when you have a 0 gradient, okay, instead of set this to be 0, we set them to be a small value. Okay, so that's a leaky. It's a very tricky design, but it works very well. Okay, so the data ReLU can be resolved by this. So the practice, okay, so you use ReLU, okay, then you try the leaky ReLU, or you try max out or another one. So do not use the sigma function or tangent function for the activation. Okay, so that's the most common practice for the activation function. Okay, sometimes maybe it's not. It may not be true. Okay, I would say. So sigma function they work very well if you have very good initialization. If it's not away from the or if you combine the sigma function with some other tricks, like the dropout trick we will introduce later, then you don't have the same trouble. Okay, so here whatever we recommend here is just some common practice. Okay, it maybe change over time. So the second one will be the pre-processing. Okay, so if you have the original data here, so for the left, so what's the challenge here? So you have one feature as the x direction, you have another feature in the y direction. So the challenge is the variance is so different. For the x direction, okay, so for the x direction, so the max value, the mean value and the max value only will be only be this narrow. Okay, but if you check the y direction, so the range is a lot more. It's a lot more than the x direction. Okay, so that means it's not even setting. Okay, it's not even setting. So the second problem will be, so the center is not around 0. So why would we prefer 0? So remember, the gradient descent will be driven by the positive or negative. Okay. So if all the data points are on the positive half, then it's possible if you initialize the parameter to be positive, that means you always have positive gradient. Then you will kill the gradient descent. So, but if you normalize, if you centralize all the data points to be 0, okay, then you kind of resolve the issue. So that's why we always want take a mean off from every single data point, okay, so that all the data points, the sum over all the data points will be equal to 0, just like this. And then you can also normalize the data. So for x direction divided by the sum, y direction divided by the sum of y, then you have this. Look, it's kind of uniform distributed. Okay, so the range over x direction and the range over y direction are roughly the same. Okay, or exactly the same. So you can do this very simple. You can use if x is the feature matrix, so you can use NP domain. You can calculate the mean, then you can take the mean off. Okay, you can take the mean off from all the data points. And then you can also, by normalizing the data, you can calculate the standard deviation and divide it by this. Okay, so you can, so that's pre-processing, okay? So this is also very important. So the third one will be the weight initialization. So basically you need to, you can use some pre-train weights, okay? So pre-train weights, instead of randomly initialize the weights, so you can use some pre-training to initialize. For example, you are working on the face recognition problem, okay? Because they are dealing with the natural facial image. And then you can use the weights of the network for classification problem. It's for a different problem. But you can use that weights to initialize the network you are going to train. The people call this as initialization. But do not use small random numbers for deep neural network. If the network you are working on is very deep, that means you have many layers. For each layer, you have many neurons. So the random numbers never work. Okay, the random number never work. So you should always consider the initialization. For example, you can pre-train a shallow network and use this network to pre-train the model. Okay. So we will take this. We will practice this sometime later by using some homework. I mean, so the pre-training process. So it's an open problem, by the way. It's a really open problem. If you check the literature, so for example, in 2015, so here, so all you need is a good initialization. So there's a research paper talking about how could you initialize your network. It's a very important problem when you try to work on some deep neural network. So another way, so whatever we discussed so far, okay, will be the highest, will have the highest priority. Okay, when you try to design a network, you should always think about this problem. So which activation function, whether I have done the pre-processing, how did I initialize the weights? The next one is even more important. We call this a batch normalization. By normalization, we mean we consider a batch of activations at some layer. So for each layer, okay, then you could have, for example, 6 or 10 activation maps. Okay, so these activations, they are simple, some individual numbers. So these numbers, they could have a different range. Okay, it could be 0, 1, they could be 100, 200, or 1,000. Okay, when you have these different numbers, we need to make each dimension, okay, unit Gaussian. That means for each dimension, we want to make them to be a unit Gaussian. That's between 0 and 1. Then the mean will be somewhere. Then you have the standard deviation. So basically, you need to compute empirical mean M and also the variance for each dimension. Okay, so basically for each dimension, basically we mean so pretty much as for each channel. Let's say you have a 6 channel, then you have 6 dimensions, for example. Then you want to make all the activation between to be some samples from the same Gaussian distributions. Okay, it's pretty much like the activations you generate. They only have what we call the relative meanings. Okay, so basically, if one activation is 1,000, okay, another activation is 900. That means so the first one is higher than the second one. That's all we got. That's all we got. Okay, but for another activation map, you have one activation could be 1, another activation could be 0.7. Okay, you know the first one is higher than the second one. But it's meaningless to compare one activation from the first map to the second to another activation from the other map. Okay, it's not comparable. Okay, but anyway, so the idea, yeah.
I understand that data.
Okay.
Activations are
Uh-huh.
So when do you normally activate?
So here's where. So after we usually put after the fully connection layer. Okay. So after the fully connection layer, let's say you only have one activation map. Okay. If you only have one, if you have more than one, you will do that separately, right? You only have one, because the fully connection layer, let's say it's a 4,000. Okay, you have a 4,000 members or 4,000 activations. Then you will calculate the mean. You will take a mean off divided by the variance. Okay, then you have the normalization. So basically, the input will be, let's say, 4,000 numbers. So the output will be 4,000 numbers as well, but you take the mean off, then you divide it by the standard deviation. Okay, so that's exactly what we mean by batch normalization. So you will put this batch normalization after the fully connection layer. Okay, fully connection layer. But then usually you can do that, and then after this, so once you normalize this linear combination value, you take this as input to do the nonlinear transformation. Okay, so basically, remember for each layer you have a z. It's pretty much the linear combination between the weights and the input. Okay, and then you have for the z, you have the sigma function. You got a here. So where did you put the normalization? You put it somewhere between them. So once you got a z, then you do the batch normalization. Then after that, you feed them into the sigma function. Okay, and the same thing. So you have another fully connecting layer. You have the batch normalization. You have the tangent layer. Okay. Then you may have a question about the grading. Okay, because once you insert this layer, you will change the flow graph. You change the flow graph. Then how could you calculate the gradient? So a good news is the normalization itself, they have a gradient. Okay, you can consider the normalization as a normalization gate. So this gate, if you check the mass, you have a gradient. It's a smoothing function. So you have it's a smoothing function with respect to the weights. Okay, so you have a gradient everywhere. So you can consider the batch normalization is just another gate. It's a normalization gate. Okay, so basically, so after fully connected or convolutional layer and before the nonlinear transformation, so the sigma function G. So then you have this. So basically, if you check the code, okay, if you check the code, so for mini batch mean, So you calculate the mean here, you calculate the variance here. Okay, so check. So the mean u is a function of x, and then so xi is a function of what? Xi will be the activation of the previous layer, right? So it's a function of w. Okay, so the sigma here is also a function of xi. So xi is also a function of the previous layer. So you could see you just have another two gates here. And then once you have the mean and the sigma on the variance, you take the mean off, then you have you divide it by the sigma. So you have the normalization layer. Okay, and then you will have the so skew and the shift. Then you have the new xi. Okay, so the input will be xi, then the output will be the new xi. Then you have the new xi fit into the nonlinear transformation. Then you have the continuity. Okay, so that's basically the batch normalization. So batch normalization is very important because the reason is when you have the linear combination. So when you have a linear combination here, the xi. So the xi could be arbitrarily bigger or smaller. Okay. If you don't do the normalization, this value will make the gradient either too big or too small. Okay. If it's very big, that means so the weights for this filter will be updated really fast. Okay. It's arbitrarily. I mean, it could be any big. If it's any smaller, for example, very similar to B0. Okay, if all the value for this activation map very similar to B0, there's no gradient at all. Okay, so that's why we need to normalize them. Okay, because all the value the mean doesn't make any sense, as I said. So if you check the one activation map, okay, even all the values are very close to B0, it still makes sense to me because I only need the relative order between the neighboring activation. Okay, if they are, I just need to know how big it is, whether it's bigger than its neighborhood. Okay, that's all. So I don't care whether it's 1,000 or 0.1. Okay, so that's why I normalize them to be 0 and 1. Sorry, to be -1 and 1, to be a Gaussian distribution basically. Which the Gaussian distribution basically have 0 mean and a standard deviation. Okay, and then I feed this into the nonlinear transformation. Okay, so then you have the batch normalization. So the paper I mentioned yesterday, the paper invented yesterday or published yesterday, basically they are talking about the group normalization. The group basically mean I haven't checked the paper, but the basic idea will be how could you group this activation map with another activation map so that they can share the same Gaussian distribution. Okay, so it will change the behavior of the normalization. Anyway, so we will talk about that. We will discuss that technique later. Okay, but the basic thing is here. You have to understand this. Otherwise, it's not only about the accuracy. It's more about the convergence speed. Okay, if you do the normalization here, because so you scale the gradient very well, then you can converge much faster. Okay, much faster. So basically the hyperparameter optimization. So that's another thing. So basically you have the convergence curve. So if you look into the curve, for example, if you look into the curve, for example, the red one, it's a good learning rate. Okay, but if you got, so basically the x direction will be to the epoch. Okay, so how many training sample you have? So iterations. Okay, more and more iterations. So the y direction will be the loss. Okay, the total loss or the average loss. So if you have the red one, that means your gradient descent is converging properly. If you have the green one, that means the learning rate is too high. Then you need to change that to be a smaller one. Okay, it still work, but it doesn't converge to a lower level. Then if the yellow one is a convergence curve, then perhaps you have a very high learning rate. So you need to aggressively reduce the learning rate. Okay, so for this one you have a low learning rate. I mean, this one you have a high learning rate. But anyway, so from this curve, so it seems the learning rate is really important. Okay, so if the gradient, because, okay, if I give you this gradient, if I give you this curve, it always means your gradient is working. So the gradient, there's no error for calculating gradient. The gradient basically can guarantee the loss function is decreasing. Okay, because if you check, it's a strict decreasing. Okay, that's good. But then the not good is, the better thing is it doesn't converge properly here. So then you need to, to fine tune the change in the learning rate. So this gives us some idea about the convergence. So the accuracy. So still over time, so basically, let's say for this iteration, then you have the current W. Okay, so given the network, so for any X, okay, so you can run the feed-forward neural network, then you can get the prediction. Okay, so you get the prediction, then you compare to the ground truth, then you got some loss. Okay, this give you the Y direction, basically give you the accuracy. So as you can see here, so over iteration, so the accuracy over the training data set, okay, it's look at somehow like this. So accuracy over the validation data set, so look like this. So what does this mean? So that means, so the algorithm, the gradient descent you are using is working properly, because over iteration, you got a much better W. You got a much better accuracy. Then that means the W is good. It's a better over time. Okay. But the better thing is the green line also tell you, even your training accuracy is better and better. The validation accuracy is not becoming better. Okay. The validation accuracy basically means this model is overfitting. Okay, this model, because you have a bigger gap. You have a bigger gap between the training accuracy and the validation accuracy. So this always means it's overfitting. So your model fits the training data very well. Then when you apply the model over the non-training data, it doesn't work very well. So if there's no gap, at all between this line and that line, then you need to increase the model complexity. That means it's underfitting. Sometimes it's underfitting, sometimes it means the training data and the validation data, they are very close, very similar to each other. Okay. But anyway, so nothing is good. So you need to carefully check and double check. What does this mean? So hyperparameter is also very important. So when we talk about a hyperparameter, we always mean the learning rate, number one. The second one will be the model complexity. So how many layers you have, and then for each layer, how many neurons you have. Okay. So we are going to dig into each component. Okay. For example, pre-processing. Okay. It always means different when you're talking about different problem. Okay. When you talk about, for example, face recognition, the pre-processing could be very different from the object detection. Okay. So we will talk about everything, but keep in mind, we should always ask ourselves, regarding this aspects. Okay. So the next one will be the advanced learning. So advanced learning means the standard gradient descent. You may run into some issues. So what if loss change quickly in one dimension and slowly in another dimension? Yeah, it's possible. So basically, when we talk about dimension, so that's it could be mean differently. Then, but anyway, if we could talk about, for example, the W, so different Ws, okay, or different channels, or different activation maps. But anyway, because the different activation map, they are so semantically they are different from each other. Okay, so then it's possible. Let's say some W, they converge really fast to the ground truth one, but other Ws converge very slowly. Okay, so basically, so what if the loss function has a local minimum or saddle point? If you have a saddle point or local minimum, then you will stuck. That means you can't really get the best solution. Okay, you can only get the local optimal. The saddle point means if you have a function like this, so you got one saddle point, another saddle point. Yeah, stable point. Yeah, it's basically there's no change around the function value doesn't change around the saddle point. Okay, so noise gradient from mini batch. So basically, so that's the potential issues. Okay, if you use all the training samples, then you have the real gradient. Okay, so if there's no noise, no outliers. But if you have a mini batch, that's approximation of the real gradient. Okay, so that's why to address all these issues, so the standard gradient descent doesn't work very well. Then you need to consider some other variants. Okay, so the very first one we call it momentum. Okay, momentum basically, so we introduce some velocity as a running mean of the gradients. So that means when you try to update the parameter W, okay, when you try to update W, so previously we only determine how to update W based on gradient. Okay, the gradient basically tell you as the current W, how bad or how good the current W is. Okay, or which way you want to go. But now we also consider the velocity, because over time, so the W will be decreased or increased over time, over iterations. So that's basically, the velocity will be also very important. Let's say over iterations, or if you look into the previous 10 iterations, okay, then I kind of slowly change W. That means what? That means you almost get the local minimum, or you are getting closer and closer to the local minimum. So for this situation, maybe you don't want to run too fast. Okay, you can change the learning rate to be a smaller one. Okay, but anyway, so the velocity will be very important. So the gradient descent method. So original one, it's a simple based on the learning rate times the gradient. Okay, but now if you consider the velocity, it's just like, okay, if I put let me give you an intuitive introduction. If you here is a slope, if you consider the current position will be here. Okay, so without even the bar, if this bar is zero velocity, so you can predict if you follow the gradients, you will go this way. Okay, but then there's no problem for this. But what about this? So if I give you a curve like this, so if you have a gradient, if I know, okay, if the current position is here, so even the velocity is zero, I can still follow the correct direction, say to the right, because the gradient is really sharp. Okay, but if the bar is here, so what happened? If you can only consider the local gradient, okay, because the gradient basically tell you should go to left. The gradients, because the shape is look like this. Okay, the shape look like this. If the ball is here, then the gradient tell you should go to the left. But if you look over the whole shape of the function, so actually I need to go to right, right? Because here I have a really big, velocity here. So when I run to here, I should consider the velocity of the previous iteration so that I can overcome this zigzag. Okay, overcome this zigzag. This zigzag is not a rare when you're dealing with a practical problem, because you are going to have many local minimum and outliers and noise. So I'm going to have many such things in the landscape. Okay, so that's what we mean by the velocity. So basically, when you try to update W, you will consider both the local gradient and also the velocity you got from previous step. Okay, if you have a really high speed like this, then the local gradient is not so important anymore. Okay, so in equation it's very simple. Okay, so you just count the gradient, the speed. Say the v is equal to the previous v times plus the current gradient. Okay, so you just, and the previous v times by the say it's basically so the rho basically is let's say 0.5, for example. It's so this guy is you can consider as a running gradient, running mean. Okay, you get one new, so let's say you got a one new gradient, then you plus 0.5 times the original space velocity. Then you have, so basically the v is kind of reflecting the current speed, or the average gradient you have in the past iterations. Okay, any question?
Is it possible that both the velocity is small, but you still cannot encounter over the local minimum?
Yeah, it's possible, but it's better. It's better than nothing. It's better than zero velocity, zero speed. So that's, you never know. You never know the answer for sure. But in general, if you consider velocity, you can overcome some small noise. Yeah. Local minimum. Yes. So basically, so you guess the, so basically this gives you the velocity. Basically, it's a mean of the gradients. Okay, in the past, let's say 10 iterations. Okay, and then you will update W, say the parameter, by learning rate times V. Okay, the learning rate times velocity. If the speed is high, then you update high. If the speed is low, you update low, smaller. So the V will be also positive or negative. Okay, if in the, let's say if in the previous 10 gradient, in the previous 10 iterations, all the gradient will be positive. So the velocity will be positive as well. If some of them are positive, some of them are negative. Okay, some of them are negative, some of them are positive. Then I just check the mean of them to see which direction you want to go. Okay, so this one is really possible. For example, if all the, let's say if you look into the previous 10 iteration, if all the gradient are positive, that means what? That means the shape really look like this. If all the gradient are negative, that means the shape look like this. If some of them are positive, some of them are negative, let's say half are positive, half are negative, that means what? Like this. Okay, so here there's negative, positive, negative, positive, negative, positive. Okay, so if you have the negative, positive thing, then I just look into the mean. I just look into the mean to see whether the mean is positive or negative. If the mean is positive, that means what? If the mean is positive, that means you got this. Okay, if the mean is negative, that means you got this. Okay, it's a zigzag, but the whole trend is still increasing. Cool. That's really, so the people really love this idea because I mean look into this situation, right? So you have a situation 1, 2, 3, and 4. Okay, you can deal with this 4th situation adaptively by only looking into the running mean of the gradients. Okay, but this one is not perfect because so the people call this, so if the gradient is in this direction, okay, the velocity is in this direction. So the actual slope will be, so you kind of take a combination between that, okay? Because based on the current gradient, you will update velocity by this. You will update the velocity by rho. So the rho basically decide how big you want to trust the velocity or how big you want to trust the current gradient. Okay. So basically, so the actual slope will be a trade-off between velocity and the gradient. If you have a really strong gradient locally, you have a very strong gradient, then the velocity will be determined by or dominated by the current gradient. Then you will go this way. You will follow the gradient. Anyway, so the Nesterov is mathematics from Russia. He's a really famous guy. His contribution is really broad. He's a genius guy. So himself, he didn't work a lot in machine learning. And if I remember correctly, he's more a mathematics guy. He developed many gradient descent like machine learning models. It become very popular in AI. So he has a small change. It has a very small change. So basically, if this is current position, so basically instead of compute velocity, okay, let's look in the equation. So the traditional way will be, okay, so the current speed minus alpha times, so basically, so here's the gradient, okay. So basically it's a running gradient, it's a running mean of the previous gradients. Then you will update the x, so the parameter by this speed, okay, by this speed. If the speed is positive, you update as positive, otherwise it's negative. So basically, you will update the parameter by using the speed, But the Nesterov, basically, they propose a new method, okay, a new method. Basically, you still have, so basically look into here. So the key idea, the key difference is, so you look into the previous, when you try to calculate the gradient, did you use the current value or you use the updated value? Okay, so if you use the updated value, okay, so basically you got the normal gradient, the normal momentum. So basically, so in this case, so you have x, the current value plus this guy, so this basically give you the velocity, okay, give you the velocity. So this give you the new w, a new x in this step. So and then you will calculate the gradient over the new step, over the new value, and then you calculate the speed, okay. But here, you pretty much you first get the gradient, okay. You get the gradient first, and then you will calculate. Okay. So that's the current speed, okay. So here's the previous speed. So here's the current speed. So basically, you kind of so update this xt based on these two things, based on the previous speed and the current speed, right? Or based on the current speed or the new speed. So basically, so the reason for this is, So the Nesterov momentum is converging much faster than this traditional one. Okay, converge much faster because you kind of utilize the gradient over the next step. Okay, so you consider the current step, the gradient of the current step. You also consider once you update that, so what's the gradient look like? Okay, it's kind of you look bigger than the previous method. But here, if you look into here, so basically you only consider the gradient of the current step. Okay, there's only one gradient to consider. But anyway, so that's the momentum. So you can consider so that's the speed and the gradient. So that's kind of a combination between that. So you also have another variant. We call it adaptive gradient. So basically the idea is, okay, you just look into the historical gradients to scale the current gradients. Yeah, instead of moving average. So basically you look into the previous iteration, say, so the current, at the beginning, the gradient equal to 0, right? So then over iteration, I will calculate the gradient dx, and then so I take a gradient as accumulate all the dx together, okay? And then, so when you update the current, let's say when you update the current x by dx, it's divided by the accumulated gradients. Okay, that means what? That means you look into the parsed window. If in the parsed window, the gradient is really big, then the current gradient will be scaled down. Okay, because that means what? That means you have a really big gradient. That means you have a very large step in the previous 10 iterations. So now you should, be careful. I mean, be careful. You need to kind of change your gradient to be smaller and smaller and smaller. But if you have a very small gradient, then I will change the gradient, scale the gradient up, and scale that to be bigger. Okay. So basically, so this term basically is used to balance. Okay, to balance the gradient. Okay. So how would this affect the gradient descent over time? So basically, that's what I told you. So basically, if you have a bigger gradient, then I want to slow down. If you have a slower gradient, smaller gradient, I want to speed up. Okay, and then it become a balance. Okay, so the people call it adaptive gradient or ADA gradient. So basically, we want the compromise. Okay. So another one is it's pretty much a decaying factor. So basically, you also use the historical gradient to scale the current gradient, but then we introduce another parameter, say the beta. So the beta you can consider. So when you accumulate the gradient, so the beta basically considered as a forgetting parameter. If gradient is equal to 0, that means what? The historical gradient doesn't work. It doesn't affect the current gradient. Okay. So basically, so you can consider beta is a forgetting factor. Okay. Larger beta means smaller beta means the past gradient doesn't affect a lot. Okay. So basically, and then you will take this same way. It's a cumulated gradient. Then you take this to divide the current gradient. You just make it adaptive. Okay. Okay. So here's the last one. Not last one. That's the best one. It's the most popular one. So the ADAM. So ADAM basically is a moment-wise gradients. You use the moments to scale the current gradient. Okay, so it's kind of a combination of the previous two variants. So once you compute the speed, okay, you use the speed to update the gradient. But now you kind of use the speed or moment to scale the current gradient, and then you introduce the two decaying factors. you have two parameters. So let's say you have two more parameters, plus the learning rate, you have 3. Okay. So basically you have beta 1. So you have a beta 1 times moment 1. So 1 minus beta 1 times the gradient. So basically that's a beta 1 determine you have moment 1, you have 1 speed. So moment 2 is also the second order speed. Okay, it's the second order speed. You have another speed. So one is for the running mean, another is running, basically the running variance, right? So it's delta square. You can consider mean of the square, basically you can consider as a variance. So you can consider as the first order speed and the second order speed. Okay. So you have 2 moments. So then you use these 2 moments to update x. So what does this mean? So can anyone tell me what does this mean? So if the moment 1 basically tell you the speed, if the speed is really high, of course I need to update. I need to use a larger step, right? But the second order means what? The second order means, because the first order basically means it's a positive or negative. Whether it's say the shape, whether it's in this way or in this way. But the second order basically tell you whether it's this shape or this shape, right? So the second order basically tell you so if you have a very sharp, you have a very sharp shape, then the second order is higher. The second order gradient will be higher. If you have a very slow shape, then the second order will be almost 0. Okay, the second order gradient. So basically, divided by the second order gradient means what? If you have a larger second order gradient, then that means what? That means I want to change x slowly. Okay, I want to change x slowly. If I have a smaller second order, I want to change x quickly, aggressively. Why?
Stabilize.
Yeah, so actually the reason is very simple. If you look into this, it's really sharp, really slow. Okay, so if you check, so x, let's say, so here's x, so here, here's x, so here's f. Okay, so if this is really sharp, that means what? So over here, even you have a very small change over x, so the x, so then the f will be changing dramatically. Okay, even you have a really small change over x, then the function value will be changing a lot because it's a really sharp area. But for over here, then what happened? Even you change x to be a really bigger one, so from here to here, then the cost value is pretty much it's the same. Okay, it's the same. That means what? To change the same amount of loss, to reduce the same amount of loss. For this case, you need to be much smaller than the normal one. For this case, you have to behave really aggressively, okay, to change the same amount of f. So that's why we need the second order moment, okay, second order moment, to divide the first moment. With the first moment basically tell you which direction you want to go. You go to left or go to right, okay. But the second order tell you how fast you want to move, okay. So that's why the ADAM is really popular, okay. It's really popular in the gradient descent, okay, in particular in deep learning, because the deep learning curve is a highly nonlinear loss function. So it's like this, it's a really nonlinear function. So then we really need, okay, if you have this shape, okay, then I need to move slowly. Otherwise, if I move normally, then I pretty much like, I may miss this local minimum. Okay, I may miss this local minimum. Anyway, so here's some magic number. So I hope you can understand this conceptually. Okay, it's very simple. But it's really smart. Okay, it's really smart to. So of course you have a beta 1, you have a beta 2, you have alpha. So you have 3 parameters. So here's some magic number. That means if you normalize your data, if you centralize your data, then they always work. For example, the alpha set to be 0.001. So the beta 1 is 0.9, the beta 2 to be 0.999. Okay, if you set them to be this, it's always work. Okay, so it's a magic number. So that's advanced learning. I mean, okay, to summarize, so the people never use a standard gradient descent in practice. Okay, they always want to change the learning rate over time based on the first gradient, the first order derivative, and the second order derivative. Okay, so there's some advanced study. There's some advanced study for this regarding this. So let's. Okay. But we will cover this again. Okay. So just make sure you understand this first. So the next one is also very important. Okay, I always say, so everything I list here is the most important thing in my mind. So I believe, I mean, so we can't say one is more important than another one. So all of them are very important. Okay, so regularization, because we are dealing with the overfitting problem. So the overfitting is always the #1 issue for deep neural network. Okay, because you have, let's say, if you look into the Google Net or the recent developed architecture, you have 1,000 layers. Each layer have 1,000 parameter. So you can easily learn a model which work on the training data very well. Okay, because you know the ground truth. Okay. So if your model is really complex, you can always reduce the training error to be 0. Okay, that's overfitting. Okay, that's mean you have 0 training error. You apply the model over the testing sample you never seen before. You got better performance. That's overfitting. So overfitting is the #1 reason we need to consider. The regularization term. So we try to use this prevent overfitting and increase generalization capabilities. So the idea is very simple. Okay, so you have some loss. Say it could be the classification loss. It could be the let's say it could be, for example, the reconstruction loss or any type of loss you have. Okay. So in addition to this, when you try to minimize the weights, say the W, the network weights, so we also try to minimize RW. So that's a regularization term. So lambda basically will determine how this term important, how important this lambda, this regularization term is. So the RW could be in different ways. For example, if we define RW as L2 regularization, okay, it's pretty much we take a sum over KL, take sum over all the possible, every single weight filter weight. We take a square over every one. So because we don't care about the positive or negative, okay. So we take a sum over the square. That means what? That means if you try to minimize this term, we hope W, the filter width, to be as small as possible. Okay. Why? It sounds like it doesn't make sense to us, right? So why would you like to make them as small as possible? Because we want to increase, on purpose, we want to increase the error. Okay. if you don't want to, if you don't have this error, if you don't have this, then the loss function will be minimized to be 0. Okay, if you overfit the data, the loss function will be 0. But now I want to increase the error of FW. I want to increase the loss of FW. So I put some restriction over the possible W values you could have. I just tell you, let's say you can't go beyond, for example, 10. Of course, you will have much larger errors, right? Because you kind of reduce the feasible region anyway. So same thing. So you could have many other reasons. The people have studied this problem for a long time. So the L2 normalization, you could have many other motivations. But here the basic motivation is I don't want to the data fit. I don't want to W fit with the data too well. Okay. So I just put a penalty here. Okay. So the L1 norm is pretty much the same. Okay, I take a sum over L1, the basically absolute value of the each filter weight. And then I have the elastic L12 norm. So basically I just take the sum over this one. So the L1 norm, they also have another effect. Okay, if you minimize the L1, minimize L1 norm, so they will make the whole parameter to be sparse. What do you mean by sparse? By sparse, I mean most of the W, imagine you have millions of W, right? If you minimize L1, if you minimize this, most of the W will be 0. So that means only a few of them will be non-zero. That's mean by sparse. So sparsity, it was really popular if you go back like 5 years ago in computer vision, machine learning, everyone is talking about the sparsity. Why? If you have a sparsity over W, then you are likely to have some meaningful patterns. Okay, that means most of the activation will be 0. Some of them, only some of them will be non-zero. So we will introduce this later because we are going to introduce sparse coding sometime later. So we talk about that. L1 regularization is really interesting. It's really interesting if you talk about the overfitting. Okay, the overfitting. Because imagine, okay, if only some of them could be non-zero, that means you can never reduce the loss function perfectly, right? You can never reduce loss function perfect. So you also have some combination between these two. Okay, that's also work. Okay, so regularization term will be the most popular way to prevent overfitting. Okay, so the number one reason is if you have L2 norm, remember, if you try to minimize this loss, okay, so the first term you have a gradient, but the second term you also have a gradient. For example, for this guy, if you calculate the gradient with respect to W, it's equal to what? If you consider this, it's equal to 2 times KL W KL. Okay, so it's just equal to, you just put this guy, or you just add this extra term in your gradient function, and you can you should have then you have the loss, you have the gradient for this regularized term. So but this guy you don't have a gradient, but you have a subgradient. Okay, the subgradient basically means you have you don't have a gradient for the 0 because that's a saddle point. There's no gradient for 0, but you do have, if you have a less than 0 or larger than 0, you have a gradient on both sides. Okay, so we talk about that later. So the number 2, or another very important trick to prevent overfitting is we call dropout. So dropout means in every forward propagation or forward pass, okay, forward pass basically have a 2-step, linear combination, nonlinear transform. Okay, so you just randomly set some neurons to be 0. you randomly set, once you have some linear combination, you just set them to be 0. So once you do the forward pass, okay, randomly pick up, let's say you have 1,000 neurons in the fully connected layer. Then the dropout ratio, for example, is 0.5. That means you randomly pick up half the neurons and set the activations to be 0. So the probability, for example, if you set them to be 0.5, you force the network to have a redundant representation. It's one way to explain that. Another way is you just force the network not to be overfit. Okay, overfitting. So at the test time, so the problem for test, so when you try to do the test time, you need to multiply by the dropout probability. Let's say if you have the activation fx, then you need to times by the probability you use to do the dropout. Okay, and the reason is actually very simple. Okay, so let me see. We will discuss this in another lecture. So why would you like to apply this factor? Okay, because we want to keep the expectation of the testing activation and all the expectation of the training activation to be the same. Okay, so for the training, let's say because when you do the training process, you have 0.5 probability to set that to be 0. Okay, you only have 0.5 to be the current value. If let's say if the activation is 5, okay, so the expectation will be what? Will be 0.5 times 5 will be 2.5, right? The expectation will be 2.5 because you have two cases. One is if you turn on, it's 5. If you turn off, it's 0. It's 0. So you have 0.5 probability times 5. So the expectation for this neuron is 2.5. And then when you do the testing, okay, then we also hope the prediction, the activation is exactly the same as the expectation. So that's why we put 0.5 times 5. Okay, so that's so then you have the value is 2.5. It's the same as the expectation. Okay. So the data, another trick. Okay, you can see to prevent overfitting, I will tell you 3 tricks. Okay, it's the most important thing because overfitting is literally the #1 issue in deep neural network. Okay, so the third one we call the data augmentation. So what do we mean by this? So the training data you have many training data, right? So for each sample, it's an image label pair. You have this image, you have a label, okay? And then, so the data augmentation basically tell you keep the label, and then you can generate some random box, okay? And then for each box, you just crop. For example, the yellow one, you just crop. And then you will resize this crop image to be as the same as the input image. Okay. In this way, for this image, you generate this we call a new data. Okay. So for each box, you will generate a new data. So it depending on how many boxes you have, you could have a few hundreds or few thousands sub-region crop like this. And all this crop region or this augmented sample, they will share the same label. Okay. So why would we need this? Because we want to create, we call the redundancy. Basically, we want to create enough data. Okay. So but this trick is really useful in practice. Of course, another question is how could you generate this trick, this random box? you can follow different principles. For example, the box should cover different portions of the image. That's number one. Number two is, so each box could have a different size. Okay, some will be 100, some will be 200 or 20 or 10. So you could have a different resolution because we have no idea about how big the human is. Okay, the target interest, the interest object, we have no idea how big they are in the image. So we need to cover all the possible, all the possible situations. Another ratio will be, so for the box, you could have this ratio. You have this ratio, you could have this ratio, you could have the rectangle. So you need to use different ratios. Okay, the width and the height should have different ratios. You can easily get like thousands. You can easily have thousands run on the box. Okay, so that's very normal. Okay, so most in our most recent project, so for one image we generate like 400 samples. So that's mean if you have 100 training samples, so now you have 40,000. You have 40,000 training samples, but most of them some of them they will share the same label. Okay, that's fine. So that means you can combine translation, rotation, stretching, shearing, distortions, color offsets. Okay, all different tricks. Okay, so anyway, eventually you want to. So basically the idea is, if you generate a lot of data, okay, if you have a lot more data, training data, you have much less chance to be overfit. Okay, to be overfitting. Yeah.
In this case, isn't there a risk that only can be tried?
Really? Yeah, it's possible. It's possible.
But also this way, there may be create some outliers in the data.
But you never know. Depends on what kind of label you have. If you say, I want to classify this image to be outdoors or indoor, so you don't have any outlier. Or you want to detect a human. If you want to detect a human, then possibly you may have outlier. Let's say if you generate a ratio like this, and then you consider, oh, this is yes, actually it's no.
Yeah.
But you remember, if you generate like a 400 label such samples, like 99% of them will be inlier. Only one of them is the outlier. It's okay. It's completely okay. Yeah. Okay. So to summarize, okay, regularization. So we talk about regularization term. Okay, so L2 term, L1 term, or L2 plus L1. Okay, so dropout. Then we talk about data augmentation. So the batch normalization, you can consider as the regularization term as well. Okay, somehow. So that's the most important thing. So the transfer learning. So that's another thing we kind of conclude this lecture. So the bigger question we want to ask is whether deep learning is equal to transfer learning. So what do we mean? What do we mean by transfer learning? Transfer learning basically is a common topic in machine learning. So let's say we're talking about two different problems. Okay, so these two problems, they are working on different data. Let's say if you try to, so for one problem, I'll give you an example. For one problem, you may like to train a detector to detect human, for example. For another problem, you may like to train a detector for detect a vehicle. Okay, so it's two different problems. So then the question will be, so if you train the detector for the first problem, okay, so you have the human detector. So whether or not, so this detector can be used to help learn the detector for vehicle. Clearly it is. The answer is always yes. Okay. So you have this pattern. Intuitively, at least, okay, if you one vehicle, that's one region, okay. If the first detector say you have a high confidence it's a vehicle, it's a human, then we'll try to learn the vehicle detector. You have some information. Say it's more likely to be human. It's not a vehicle. Okay, so at least you have such such coupling relationship between these two problems. But actually, transfer learning is more of the many other things. For example, if you train a vehicle detector by using the data in daytime, okay, so you have very good lighting condition, you have the colorful vehicles under sunshine, so you have to train a detector. Then the problem will be whether you can apply this detector over the nighttime. So there's no sunshine, no lighting condition, no strong lighting, right? Then the vehicle look like gray, most of like really, really dark. So how could you utilize the detector you train to help with the second problem? Okay, that's the transfer learning stuff. So the deep learning, at least some people in the academia, they believe deep learning is a sort of transfer learning. The success of the recent deep learning method is more or less related to the schema it uses for transfer learning. For example, you can train this neural network, okay? So I just put the network architecture. You have an input image, you have a convolutional layer, max pooling layer, another convolutional layer, max pooling layer. So anyway, you have a really deep architecture, okay? Then you can train this network on the ImageNet for the classification problem, okay? Classification problem, basically the final layer will be 1000. That means you try to classify this image to be one of the 1000 categories, okay? And then there's a small data set. Let's say after that, I want to build up the face recognition. So everyone send me a set of face photo, right? So I want to build up a network to detect the face. But I only have a very small data set. Okay, so then I can reuse this network. So remember, this network I have trained it. Okay, and then I will freeze this part. Okay, so that's not change. Okay, so basically I keep all these parameters to be the same, but I only fine tune the last one, the last layer. So the last layer, they have 1000 neuron. But how many parameters you have? You have in the previous layer, you have 4096. So for this guy, you have 1000. That means you have 1000 times 4000, right? It's a fully connected layers. So you have 4000 times 1000. So literally, you already have 4 million. You have 4 million parameters. So I only change this layer. I kind of change this layer by using a small data set. I won't change this part. Okay. So that's kind of the transfer learning. So basically, so for this one and this one, I make assumption. Say these two networks share the previous most of the network. Okay, but the last layer will be different. Width, no, you don't change the width. When you train, you only change the width of the last layer. That's it. So you just stop. When you change the last layer, the parameter of the last layer, then you just stop. As a featureization, yes. Basically, you consider these features has been learned in this over this largest scale data set. So the reason is if you have a small size data set, okay, you don't have enough data or information to train all this deep neural network. Okay, so that's mean so you are likely to overfit if you train the network from scratch. Okay, but if you don't change, if you freeze this, okay, if you freeze this, then you kind of have a very good, you have a very good low-level representation, but you still have the capability to deal with this small data, this specific data set. Okay, but that means we have a small data set. What if you have like a thousands or even 10,000 data set, a larger data set? Look, so that's the trick. So you kind of freeze a smaller portion of the network, but it's still majority part of the network. But you try to fine tune this small part. So you kind of retrain 3 layers instead of 1 layer. So here you have 1 million parameter, but here how many you have? I mean, potentially you could have 16 million parameters, right? Potentially you have 16 million. If you have 1,000 here, so it kind of, I mean, that's mean because I have a relative larger data set, so I can potentially, even I try to retrain this amount of parameter, it won't overfit. But I have we don't have a math or equation to tell you based on the size of the data set, how many layers you want to fine tune. Just give you an overall idea. Okay, if it's relatively small, you fix most of them. If it's relatively larger, then you kind of retrain some of them. So because this kind of based on the observations, the rows of layers. So the lower level, so the layers closer to the image, okay, layer 1, layer 2, layer 3 is more generic. But the layers of the upper layer is more specific. Okay, in particular for this 1,000 layer, 1,000 units. So the first unit is for the first layer, first class. The second unit is for the second class. The third one is for the third class. So it's very specific. But the layer here, if you look into the neuron in the first layer, so this neuron, it could represent some localized texture or patterns. So this texture could be shared by all the 1,000 classes. Okay, so it's more generic. So the texture or the filters you use here is more generic than the previous one. So then the bigger question is, how many data do I need to train a decent neural network? So here's the table. Okay, you can check the table. So basically, if you have a little data, okay, you have a very similar data. That means similar data means the pre-trained network, the data set you use for pre-training are very similar to the data set you are working on. Then you can use a linear classifier plus top layer features. But it's not similar. You can use some linear classifier. Okay, but if you have a lot of data, okay, so what does this mean? You may not get it. What does this mean? If you have very little data, the idea is, so you will fix this, most all the layers, okay? And then for any image here, you will have 1,000 numbers as output, okay? So basically you have too little data to train any decent network. So I don't do any training. So I basically, given the pre-trained network, I just threw this image, I got this 1,000 activations. So I use this 1,000 activations as 1,000 features to represent this image. And then that means for every single image, I have this 1,000 feature dimension vector. And then I use, for example, the linear classifier, could be SVM, or could be a linear model, any linear model you could imagine. And then plus the top layer features and do the classification. I say if you work on 50 facial photos, okay, so you can use this method. That's no training at all. Okay, so if you have a not similar data, okay, if the data is not even similar, okay, so you just use the linear classifier. Do not use any network. Okay, you just take this data plus some linear classifier, then you are done. Okay, because there's no way to reuse this pre-trained model. Okay, but if you have a lot of data, then you can fine-tune at few layers. Okay, the new task you are working on, you have a lot of data. So you can fine-tune some of the layers, top layers. But if you, as long as they are similar to each other, okay, so you are fine-tune a few layers. But if the data are not so similar, let's say the training the pre-trained network, for the pre-trained network you work on the daytime vehicle data, okay? For the new task you are working on, you are working on for example, the nighttime vehicle data. They are so different. Okay, so different. That means what? Then you need to fine-tune multiple layers. Where you have a lot of data, so you can certainly fine-tune a lot of layers. Okay, so that's a general table. This table is really really smart. So let's cover some different situations. So anyway. So if the data set of interest has less than 1 million, okay, in general, we are talking about in general. So 1 million is a magic number. If you let's say if you don't have 1 million data, so in general, you have no way to train a decent neural network. Okay. So here's some trick. So you can find a very large data set that has similar data, but a lot more data. So when we talk about the image, we're not talking about the raw image. We're talking about the label image. Okay, for this image, if you work on like a face recognition, I mean the training image, you know the labels. So the data is not so difficult to get, but label is very difficult to get. Okay. Then you can train a really big convolution network, and then you transfer learn on your own data set. Okay, that's the number one practice when you work on, for example, let's say if you go to some company, most likely if your company is not Google or Baidu or like a Facebook, okay, so you are likely to work on a very small data set, okay. Then how could you develop your system? So here's the way, okay, you can utilize, let's say if you work on face recognition, so you can check the existing face recognition data set, use that to pre-train your model, and then you fine-tune your model. But make sure, so the number one solution will be talk to your boss and get more data. So if you get more data, then you pretty much solve the problem. Okay, but most likely if you cannot get a lot of data, then here you have some tricks at least. So that's a summarize. Okay, that's summary. So if you summarize, so for all these components, I always say, oh, this one is very important. So, but in fact, they are very important. Okay, every single one is very important. Because just give you an idea why they are so important. Because like 50 years ago, the people already know convolutional neural network, but they never make it really work. Okay, until like 5 years ago, the people, a really genius guy from Professor Hinton's group, he kind of developed some guidelines for all this. Okay, he developed some guidelines. He didn't invent any new concept, any new technique, but he just come out a guideline. If you do this, do this, do this, do this, then you got a 20% improvement. Okay, that's it. But the 20% means it's not for one specific problem. It's for all the problems we are working on, like a computer vision, machine learning, like speech recognition. For all this problem, if you do this trick, you can improve a lot. Okay, so that's why we say. So you have some. If you use some like a TensorFlow, some existing deep learning library, you have to. I mean, that's good. If you write your code from scratch, you are likely to fail. Okay, because I mean the people already failed for 30 years. I mean, so there's no way for you to write the code from scratch. Okay, so but good news is so nowadays they have so many deep learning package, so you can easily tailor the library to your own problem. But anyway, to summarize, so for computer vision part, so we talk about DG recognition, multicast image classification, learning-based feature extraction. Okay, learning-based. The machine learning part, we talk about the feed-forward neural network and the convolution neural network. The problem solving, so basically we'll talk about the network implementations. So this is just on time, but we don't have time to go through the homework full. So maybe you can take this week. Okay, take this week to finish the homework 3. Okay, homework 1 and 3, and look into the code I give you here. So it's a lot of work here. But from next week, then we will work on the homework 4. Okay, homework 4 is very important because we are going to test a few cases. If you have interest, I can also share. I can also share the homework 4 for you. So anyway, I will upload the slides. So the homework 4 is very important. So basically, so basically it's a summary. You can check here. So that's something. So far we already learned. Okay, most of them we give you the code. Some of them we ask you to do that on your own. But in this homework, pretty much we try to test the different combinations. Okay, so problem 1, 2, 3. So basically, give you some. I'll give you some ideas. Say how could you develop some decent deep learning system. Okay. Anyway, so if you have time, I will upload this to the Google Drive. Then if you have time, just make sure you look into that. But I need your facial photos by the end of Sunday. If you send that to me, homework 3, yeah. Then if you send that to me by the end of Sunday, then I will assemble them together and share to everyone. So you can work on the homework 4. Okay. Okay, that's it. Let's so stop.